Hello everyone, thanks for being here. Thanks to the organizers, and I also would like to thank Professor Rukmini, Professor Ramshankar Gupta and Sam for useful discussions whenever required. The title of my talk is Yamabe solitons on Sol 3 space, where Sol 3 is three-dimensional solvable Lie group. So the collaborator in this work of mine is Professor Ramshankar Gupta. These are the contents. So the aim of this work is to find the existence, known existence of Yamabe solitons and gradient Yamabe solitons on Sol 3 space with left invariant Riemannian and Lorentzian metric. So this talk is based on the following research paper, and this work was dedicated to the memory of Professor Dr. Kishan Lal Duggal. So Thurston gave a classification of three-dimensional homogeneous manifolds into 8 model spaces, which are real space forms R3, S3, S3, having group of isometries of dimension 6, and S2 cross R, H2 cross R, nil 3, the Heisenberg group, the universal covering of SL2R, having group of isometries of dimension 4, and Sol 3 space with a group of isometries of dimension 3. The Sol 3 space is a simply connected homogeneous three-dimensional manifold having the smallest number of isometries, which makes it more intriguing to study. One more important thing about this is that out of 8 geometries of Thurston, this is the only geometry which is not rotationally symmetric. So which makes it more interesting to study. So the Poincare conjecture is a special case of Thurston conjecture which states that every compact orientable 3 manifold has a canonical decomposition into pieces that each have one of the 8 type of geometric structures. There have been extensive studies to understand this type of problem, but the important efforts are due to Richard Hamilton because he introduced both the Ricci flow and the Yamabe flow to solve some of the open problems. G. Perelman gave a proof of Thurston conjecture using Ricci flow technique, and hence for this technique attracted the attention of researchers to study problems in homogeneous spaces. Although most of the work has been done in the Riemannian settings using the Ricci flow techniques, but in last decade many people studied in Lorentzian settings also. So Ricci flow is well posed in Riemannian settings, but it is ill posed in Lorentzian setting. Well posed means that its solution of PDEs will exist, solution will be unique, and it will be stable. That for small changes it will not change much. So now Yamabe flow, same as Ricci flow, is well posed in Riemannian setting, which may not be true in Lorentzian case due to the non-existence of short time solutions in general because of lack of parabolicity, because in this case we will get hyperbolic PDEs, so that's why there can be some problems in solutions. So on a smooth Riemannian manifold M with initial metric G naught, the evolution of the metric G naught in time t to G is equal to GT through the equation this is the equation of Yamabe flow. Here R and G are depends upon t, and G naught is the initial metric at time 0. Yamabe flow is significant as it is a natural geometric deformation to metrics of constant scalar curvature. A Yamabe soliton on a complete Riemannian manifold satisfies half of LVG is equal to nu minus RG, where LV is the Lie derivative along the smooth potential vector field, G is the Riemannian metric, nu is the scalar, and R is the scalar curvature. So there are many solutions of Yamabe flow, but one of the special solution of Yamabe flow is Yamabe soliton, which is the Yamabe flow of Hamilton, which develops along the symmetries of the flow, and the soliton is steady, shrinking or expanding as nu is equal to 0, greater than 0 or less than 0 respectively. If the potential vector field is equal to gradient of some real valued infinitely differentiable function f, then it is called gradient Yamabe soliton, and if v is killing, then Yamabe soliton is called trivial Yamabe soliton. Many researchers have done work in this direction. So some of the works are as follows. Calvino and Luzau gave a geometric characterization of Yamabe soliton on three-dimensional homogeneous Lorentzian manifolds, and Daskalopoulos and Sisam classified locally conformally flat gradient Yamabe soliton with positive sectional curvature. Nito and Tenenblatt investigated gradient Yamabe solitons conformal to an n-dimensional pseudo-Euclidean space, and recently Sheikh et al. Characterized gradient Yamabe solitons with some additional condition. As I told that in gradient Yamabe soliton, we take the potential vector field V as gradient of some infinitely differentiable function f. So some facts about solvable three-dimensional solvable Lie group. So the Sol3 space is defined as a group of 3 cross 3 matrices with the group structure given by this. So we denote by nabla and R the Levi-Civita connection and the Riemann curvature tensor of Sol3G respectively, such that Riemann curvature tensor is given by this formula and Ricci tensor is obtained by this formula. Here we have to take care of this thing because in Lorentzian there can be change of sign. It can be +1 or -1. So we have to take care of this thing here also. So first we examine the existence of Yamabe and gradient Yamabe soliton on three-dimensional solvable Lie group Sol3 with the Riemannian metric. So we consider here the left invariant Riemannian metric. Both type of metric, left and right invariant metric exist, but left invariant metric are more compatible with algebraic and other geometric conditions. So we choose left invariant one. So left invariant Riemannian metric on Sol3 is given by 1.2 and we consider left invariant orthonormal frame E1, E2, E3 given by this. So now in this case, the non-vanishing Lie brackets are Lie bracket of E1, E3 is equal to E1, E2, E3 is equal to minus E2. And using the metric Levi-Civita, this Lie brackets, we find that Levi-Civita connection is given by this. So now we will find the using the Riemann curvature tensor formula and the Ricci tensor formula, we find that non-vanishing components of Riemann curvature tensor and Ricci tensors are given by this equation. So by contracting the Ricci tensor, we find that in this case, scalar curvature will be equal to -2. So here scalar curvature is -2. Now what we consider? We consider we consider that this is the potential vector field on the manifold. So here we take V is equal to F1E1 plus F2E2 plus F3E3, where F1, F2 and F3 are smooth function of X, Y and Z, and E1, E2 and E3 makes orthonormal frame. So here we denote the coordinate axis by del X, del Y and del Z. So now the result is the Sol3 space with the left invariant Riemannian metric given by 1.2 satisfies the Yamabe soliton equation. The Riemannian metric I defined earlier is equal to, satisfies Yamabe soliton equation. LVG is equal to 2 into -2 minus R into G. And this potential vector we obtained after solving the equations. So here alpha 1, alpha 2 and delta 4 belongs to R. Moreover, the left invariant Riemannian metric is an expanding Yamabe soliton. So here I give a brief proof. So using the metric and the potential vector field we defined, we find that Lie derivatives are given by this 1.9. And using the previous equations, we find, and using this in Yamabe soliton equation, we find that Sol3G is a Yamabe soliton if it satisfies the following system of equations. So here we have to find F1, F2, F3 and nu. So after solving these equations, we find that F1, F2 and F3 are given by this and nu is equal to -2. As I told, if it will be less than 0, then soliton will be expanding. So in this case, Sol3 will admit expanding Yamabe soliton with vector fields given by this 1.16. So now the next result is about gradient Yamabe soliton. In this also, the Sol3 space with the left invariant Riemannian metric given by 1.2 satisfies gradient Yamabe soliton equation, where the potential function f is constant. So in this case, what we consider V is equal to gradient of f. We already obtained, and using gradient of f, we find these equation 1.17, 1.18 and 1.19. After solving this, we will get that f is constant. So in this case, in Ricci soliton case, gradient Yamabe soliton, gradient Ricci soliton don't exist. So but in this case, we find that gradient Yamabe soliton exists on Sol3. So now we examine the Lorentzian with perspective of Lorentzian metric. So in this case, we consider left invariant Lorentzian metric, and that's left invariant orthonormal frame given by this and the non-vanishing Lie brackets. So after using this, we find the Levi-Civita connection, Riemann curvature tensor and Ricci tensor, and the scalar curvature of Lorentzian Sol3 Lie group. After using this, we obtained this result that in this case also the Sol3 space with the left invariant Lorentzian metric given by 1.22 satisfies a Yamabe soliton equation with potential vector field given by this, where beta 1, beta 2 and gamma 4 are real numbers. Moreover, the left invariant Lorentzian metric is an expanding Yamabe soliton. And in this case also gradient Yamabe soliton exists, and gradient Yamabe soliton equation is this, and the potential function will also be constant in this case. So now in future, we are planning to work on this following things, that to study and analyze the geometric structures in Sol 3 with Schouten when Kempen connection, and to analyze Liouville surface in Sol 3 space. So these are the references.
If not, can you go a little bit back where you were showing some initial requirements or the solutions to be existence of the solutions?
This you.
Back.
Okay, okay. This one you are saying. Wait a minute. This you want to say, that parabolicity, lack of parabolicity.
What does that exactly mean?
Like when we talk in Riemannian setting, then we get the PDEs, partial differential equations. That will be parabolic. But when we come to Lorentzian setting, it can be hyperbolic. So because of being hyperbolic, there can be one of the problem can exist, or all problem can exist. The solution will not exist, or if it will exist, it will not be unique. And if it will be unique, then it will not be stable. That for small changes, solution will be very different than previous one. So this type of problems can occur when we go to Lorentzian case. So that's why we want to study that whether such kind of problem will exist in study of solitons or not. If exist, then what problems we will face. So because in that, when we talk about gradient Ricci solitons, so that won't exist in like it's Sol 3 space. But when we talk about gradient Yamave soliton, it exists, and we find that in that case potential factor function f will be constant. But it is not necessary in this particular structure it is constant. It can be some variable also. So it depends upon the structure we are studying.
Thanks. Since there are no questions, I would like to thank Savita for such a wonderful talk.